Have you ever been standing at an intersection when a fully loaded semi pulls up beside you and heard that distinctive hiss and exhale of air as the driver brings 40 tons of steel and freight to a stop? Because that sound, that particular pneumatic exhale that every truck driver and every person who has spent time around heavy trucks knows immediately, is not just a mechanical quirk. It is the signature of a braking system that was chosen over every alternative for reasons that go far deeper than habit or tradition. And those reasons, when you actually dig into them, turn out to be some of the most interesting engineering logic in all of commercial vehicle design. Because here's the thing. The car you drove to work this morning uses hydraulic brakes. The pickup truck in the next lane uses hydraulic brakes. Hydraulic braking systems are reliable, well understood, relatively simple, and they work beautifully across an enormous range of vehicle applications. So why, when engineers sat down to figure out how to stop a vehicle weighing 40 tons moving at highway speed, did they look at hydraulic brakes and say, not good enough? Why did they choose a system built around compressed air instead, a system that requires an onboard compressor, air tanks, dryers, valves, and miles of airlines running through a vehicle combination that can stretch to 25 meters or more? The answer is a combination of physics, fail-safe engineering philosophy, the particular demands of vehicles that pull detachable trailers, and one absolutely critical safety principle that, once you understand it, makes the choice of air over hydraulic feel not just logical but inevitable. Stick around, because by the end of this video, you will understand exactly why every serious heavy truck in the world uses air brakes, and why that is almost certainly never going to change. Before we can understand why hydraulic brakes are not used on heavy trucks, we need to understand how they work on the vehicles where they are used. Because hydraulic braking is genuinely elegant in its simplicity, and appreciating that elegance makes it easier to understand where its limitations appear. A hydraulic brake system works on the principle that fluid is incompressible. When you press the brake pedal in a car, you're pushing a piston into a master cylinder filled with brake fluid. Because the fluid cannot compress, that pressure transmits instantly through the brake lines to the wheel cylinders or caliper pistons at each wheel. Those pistons push the brake pads or shoes against the rotor or drum. Friction converts kinetic energy into heat, and the vehicle slows down. The system is closed, self-contained, and requires no external power source beyond the driver's foot. It is mechanically simple. It is highly responsive, and it scales well across a wide range of vehicle sizes, from a small hatchback to a large pickup truck. The hydraulic principle handles the force multiplication beautifully, allowing a relatively modest pedal force from the driver's foot to generate enormous clamping force at the brake caliper. For passenger vehicles and light commercial vehicles, this system works exceptionally well, but as vehicle weight increases, as the braking forces required grow, and as the complexity of the vehicle configuration changes, hydraulic braking starts running into walls that engineering cannot easily push through, and heavy trucks hit those walls hard. Here's the fundamental physics problem. Stopping a vehicle requires converting its kinetic energy into heat through friction. The amount of kinetic energy that needs to be converted is proportional to the vehicle's mass and the square of its speed. Double the speed and you quadruple the kinetic energy. Double the mass and you double it. A fully loaded semi-truck combination weighs up to 36,000 kilograms in the United States and up to 40,000 kilograms under European regulations. Compare that to a family SUV weighing around 2,000 kilograms, and you're dealing with 18 to 20 times the mass. The braking system on that truck needs to generate 18 to 20 times the force, applied across multiple axles, managed consistently across a vehicle combination that can be 25 meters long, under conditions ranging from empty running to full gross weight, from sea level to mountain passes, from cold mornings to brake heating descents on long alpine grades. A hydraulic system scaled to generate that force would require either enormous master cylinders demanding physically impossible pedal forces from the driver, or complex hydraulic assist systems, adding significant weight, cost, and potential failure points. And even a perfectly scaled hydraulic system would face a problem that no amount of scaling can solve: the trailer problem. This is the insight that sits at the heart of why air brakes exist, and it is the one that most people have never thought through. A semi-truck is not a single vehicle. It is a tractor connected to a trailer through a coupling point, the fifth wheel that allows the trailer to be detached and reattached as needed. The tractor might pull 100 different trailers over the course of a year. Each trailer needs its own brakes, because the trailer carries a significant portion of the total vehicle weight, and without trailer brakes, the tractor brakes alone cannot safely stop the combination. Now, think about what connecting a hydraulic braking system to a detachable trailer would require. Every time a tractor couples to a trailer, the hydraulic brake circuit would need to be connected and sealed, with hydraulic fluid under pressure flowing through the coupling point. Every time the tractor decouples, that connection would need to be broken cleanly, without losing significant fluid, without introducing air into the system, and without contaminating the fluid with moisture or debris. Do that connection and disconnection cycle hundreds or thousands of times across the working life of a tractor, in truck stops and loading docks and staging yards at all hours and in all weather conditions. And the potential for leaks, contamination, fluid loss, and system failure becomes genuinely alarming. A hydraulic system that loses fluid loses braking capacity. A small leak that goes unnoticed can result in brake fade or complete brake failure under high demand conditions. The consequences of brake failure at highway speed in a 40-ton vehicle do not need to be spelled out. Air solves this problem elegantly. The airline connections between tractor and trailer. The glad hands that drivers connect with a simple twist and lock motion carry compressed air, not pressurized fluid. If an airline leaks, the compressor makes up the pressure. If the connection is made imperfectly, the worst case is reduced air pressure that the driver can detect and correct before driving. And if the connection separates completely while driving, something that should not happen but can in accident scenarios, the system responds in a way that is critically important. We will come back to that in a moment. Here's the engineering principle that, once you understand it, makes every other consideration feel secondary. It is called fail-safe design, and it is the reason air brakes are not just preferred for heavy trucks, but are essentially the only responsible choice for vehicles of this size and weight. In a hydraulic brake system, the brakes are applied by pressure. You push the pedal, pressure builds, brakes apply. If the system loses pressure, through a leak, a line failure, or fluid loss, the brakes do not apply. The vehicle has no brakes. This is called a fail-open system, and in a passenger car where the driver has time to react and the vehicle's weight is manageable, the risk is serious but survivable in many scenarios. In a 40-ton truck, it is catastrophic. Air brakes on heavy trucks work on the opposite principle for the parking and emergency brake systems. The spring brakes, which handle parking and emergency braking functions, are held off by air pressure. When air pressure is present, compressed air holds a powerful spring in the compressed position, keeping the brake released. When air pressure drops, the spring releases and the brake applies, automatically without any action from the driver. Without any electrical signal, without any hydraulic fluid, this means that if a heavy truck loses air pressure, the brakes do not release. They apply. The truck stops. This is the fail-safe principle at its most elegant. The system is designed so that the failure mode is stopping rather than runaway. A truck that loses its air pressure comes to a controlled stop. It does not career down a highway with no braking capability. This principle extends to the trailer connection. If the airline between tractor and trailer breaks or separates, the trailer loses air pressure. The trailer's spring brakes apply automatically. The trailer stops, or at least slows dramatically, rather than continuing to push the tractor from behind with no braking force of its own. In an accident scenario where the tractor and trailer separate, the trailer does not become an uncontrolled projectile. It slows itself. No hydraulic system can replicate this behavior without enormously complex and expensive additional safety systems. Air brakes achieve it inherently through the fundamental physics of how the system is designed. It is not a feature that was added to make air brakes safer. It is a consequence of the basic operating principle, and it is irreplaceable. Now that we understand why air brakes exist, let us talk about how the system actually works in practice. Because the engineering behind a modern air brake system is more sophisticated than most people realize. Every heavy truck equipped with air brakes has an engine-driven air compressor, typically mounted on the engine block and driven off the accessory drive. This compressor continuously replenishes the air supply in a series of storage tanks, typically holding enough compressed air to make multiple full brake applications even if the compressor stops working entirely. The system operates at pressures typically between 100 and 130 pounds per square inch, which is enough force to actuate large brake chambers at every wheel position on both the tractor and trailer. Before the compressed air reaches the brake chambers, it passes through an air dryer, which removes moisture from the compressed air. This is critically important because moisture in an air brake system can freeze in cold temperatures, blocking lines and preventing brake application. or can cause corrosion in the tanks and valves. A properly functioning air dryer keeps the system dry and reliable across all operating temperatures. The brake chambers themselves convert air pressure into mechanical force. On the service brake side, when the driver presses the brake pedal, a treadle valve meters air pressure to the brake chambers proportionally to pedal force. More pedal pressure, more air pressure, more braking force. The system is progressive and intuitive, giving the driver genuine modulation capability rather than an on-off response. At the brake chamber, that air pressure pushes a diaphragm that moves a push rod, which rotates the brake cam or actuates the disc brake caliper, pressing friction material against the drum or rotor. The simplicity of this mechanical chain from compressed air to friction, with no hydraulic fluid, no electronic control required for basic operation, and no complex mechanical linkages, makes the system robust and maintainable in a way that more complex alternatives struggle to match. Here is a characteristic of air brake systems that makes them particularly well suited to the multi-axle configurations of heavy trucks, and that hydraulic systems handle less gracefully. Air pressure distributes evenly through a pneumatic system regardless of how many branch points or how much distance the air travels through the lines. A heavy truck combination might have 18 wheels across 5 or more axles, spread across a vehicle combination up to 25 meters long, distributing braking force evenly to all of those wheels, adjusting for load distribution between axles and maintaining consistent response times from the front steer axle to the rearmost trailer axle is a complex fluid dynamics problem. Air handles this naturally. The pressure at the end of a long airline run to the rear trailer axle is the same as the pressure at the front axle, adjusted only for the slight response time difference from line length, which is managed through careful system design. Adding more axles to an air brake system means adding more brake chambers and more airlines, not redesigning the pressure generation and distribution architecture from the ground up. Hydraulic systems, by contrast, become increasingly complex as axle count grows because the fluid volumes and pressure requirements scale with the number of actuators in the circuit, and managing consistent response across large vehicle combinations with many axles requires sophisticated proportioning and control systems that add cost, weight, and potential failure points. Modern air brake systems on heavy trucks are equipped with anti-lock braking systems (ABS) that work with the air brake foundation to prevent wheel lockup during hard stops. And the integration of ABS with air brakes is worth understanding because it represents a significant leap forward in the stopping performance and stability of heavy vehicles. Wheel lockup during heavy braking is dangerous in any vehicle, but in a heavy truck it creates specific and serious problems. A locked steer axle wheel means the driver has lost steering control. A locked trailer wheel can cause the trailer to swing sideways, creating a jackknife scenario that is one of the most dangerous situations in highway trucking. ABS prevents lockup by rapidly modulating brake pressure at individual wheels, applying and releasing brake force many times per second to keep each wheel rotating at the threshold of maximum braking efficiency. In an air brake system, this modulation is achieved through electronically controlled solenoid valves that can vent and restore air pressure to individual brake chambers faster than any mechanical valve could operate. The result is shorter stopping distances, maintained steering control during emergency stops, and dramatically reduced jackknife risk in situations where pre-ABS trucks would have lost control. The electronic stability control systems that are now standard or required on new heavy trucks build further on this foundation, adding yaw sensors and lateral acceleration measurement to the ABS architecture, and using that data to apply individual wheel brakes automatically when the system detects an impending rollover or loss of directional stability. These systems have measurably reduced heavy truck accident rates in the years since their introduction, and they all depend on the precise, fast, electronically controllable air brake foundation underneath them. Here is a practical dimension of the air versus hydraulic question that deserves its own attention. Heavy trucks are commercial working machines that operate under demanding conditions, accumulate enormous mileage, and need to be maintained economically across their working lives. The maintainability of the braking system is not an afterthought. It is a significant factor in the total cost of ownership calculation that fleet managers and owner-operators live by. Air brake components are, in general, robust and straightforward to service. Brake chambers are replaced as units when they wear or fail, a process that a competent mechanic can complete relatively quickly. Brake shoes or pads are replaced on a schedule driven by wear measurement. Airlines are inspected and replaced when cracked or damaged. The air dryer cartridge is serviced at regular intervals. None of these tasks requires highly specialized tools or knowledge, and the parts are standardized across manufacturers in ways that make them widely available and competitively priced. The standardization point is particularly important. Air brake system components in North America are largely standardized through industry agreements, which means a part from one manufacturer fits a system built by another. For a fleet operating trucks from multiple manufacturers, or for an owner-operator dealing with a roadside brake issue, in a location far from their home shop, that standardization is enormously valuable. Hydraulic brake systems on heavy vehicles, had they been developed to the required scale, would not have benefited from the same decades of standardization. They would have required more specialized fluid management, more careful contamination control, and more complex procedures for bleeding and servicing the system, particularly across the tractor-trailer junction. For someone who has only ever driven vehicles with hydraulic brakes, the experience of operating air brakes for the first time is distinctive enough to require a learning period, and understanding that difference is part of understanding why the system works the way it does. The most immediately noticeable difference is the response characteristic. Hydraulic brakes respond almost instantaneously to pedal input because fluid is incompressible and transmits pressure at effectively the speed of sound through the lines. Air brakes have a slight delay called brake lag between pedal application and full brake force at the wheels because compressed air takes a finite amount of time to travel through the lines and build pressure in the brake chambers. In a well-maintained system on a modern truck, this lag is small, typically a fraction of a second, but it is perceptible to a trained driver and it affects how they manage following distance and anticipate stops. Experienced truck drivers compensate for this characteristic intuitively building their braking timing around the system's response. They are looking further ahead than a car driver, planning their stops earlier, and using progressive braking technique rather than the last-second heavy applications that work adequately in a passenger car. This anticipatory driving style is one of the marks of a genuinely professional truck driver, and the air brake system's characteristics are part of what trains that anticipation. The modulation of air brakes, the ability to apply precise and graduated braking force through careful pedal control, is something that skilled drivers develop into an art form, particularly on long mountain descents where managing brake temperature and maintaining vehicle control simultaneously requires a level of feel and judgment that goes beyond the mechanical. Experienced drivers use engine braking, exhaust brakes, and careful air brake modulation in combination to descend grades that would destroy brake systems applied carelessly, and the air system's progressive response is part of what makes that skilled management possible. Here's a data point that should settle any remaining doubt about whether air brakes are the right choice for heavy trucks. Every country in the world that has a significant heavy trucking industry uses air brakes on its heavy vehicles. Not most countries, every country. European trucks use air brakes. Australian road trains use air brakes. The heavy trucks of Japan, South Korea, China, India, Brazil, and every other significant freight economy use air brakes. The specific standards and regulations vary by jurisdiction. The component suppliers vary, the vehicle configurations vary enormously, but the fundamental technology choice is the same everywhere. This is not coincidence or cultural inertia. It is the result of every serious engineering tradition that has examined the problem of stopping heavy vehicles reaching the same conclusion through their own analysis. The fail-safe principle, the trailer connection advantage, the scalability across axles, the robustness and maintainability, the standardization that decades of widespread use creates, all of these factors point in the same direction, regardless of which engineering tradition is doing the pointing. When every approach to a problem independently arrives at the same solution, that solution is almost certainly the right one. Air brakes for heavy trucks are that solution. So why do semi-trucks use air brakes rather than hydraulic? The real answer is that the question almost answers itself once you understand the scale of the problem being solved. Stopping 40 tons safely, consistently across a detachable trailer combination in a system that fails safely rather than catastrophically, that can be connected and disconnected thousands of times, that distributes force evenly across 18 wheels on multiple axles, that maintains function in extreme temperatures and demanding conditions, and that can be serviced economically anywhere in the world by a competent mechanic with standard tools. That is not a problem that hydraulic brakes were designed to solve. It is a problem that air brakes were built for from the ground up. The hiss you hear when a truck pulls up beside you at a light is not just a mechanical sound. It is the exhale of a system that has been refined over decades to do one of the most demanding jobs in all of engineering, reliably, safely, and efficiently. millions of times a day on highways and mountain roads and loading docks across the entire world. And the next time you hear it, you will know exactly why it sounds the way it does and exactly why nothing else could do the job as well. What part of air brake technology surprised you most in this video? Drop it in the comments below. We genuinely want to know. Thanks for watching Titan Haulers, and remember to subscribe for much more.